spin of the electron. So if you remember, spin is a property, it could be in the classical sense. But in the quantum mechanical sense, how do we appreciate spin and put electron spin जो हमारे पास है तो ये है कि फॉर एग्जांपल it was seen that when electrons used to जो स्पेक्ट्रल एनालिसिस इलेक्ट्रॉन आता था फॉर डिफरेंट एटम्स but it was seen that when the atoms became more complex उनके एटम नंबर ज्यादा हो जाते हैं तो जो हमारे पास स्पेक्ट्रल लाइंस आते हैं they come more than what is there. For example, an electron goes from transition up to down or down to up. ठीक है, either photon is released or photon is absorbed. So you can have one spectral line. But it was seen that there were more than one spectral line. So uska explanation, how could we explain those things in that sense? So उसी को हम कहते थे. So if you, for example, an electron goes from n to 3 to n is equal to 2. For example, transition. So if there are more than one spectral lines which are associated with it, so people thought that there is something called did not think an effect was discovered. जिसको कहते हैं Zeeman effect. Have you heard this Zeeman effect? सुना है? तो Zeeman effect में ये है कि अगर किसी होमोजेनियस मैग्नेटिक फील्ड में हम इलेक्ट्रॉन को लाते हैं, देयर कम एक तो अपनी स्पेक्ट्रल लाइंस, देयर इज वन मोर स्पेक्ट्रल लाइन व्हिच कम्स एसोसिएटेड विद इट. दैट स्पेक्ट्रल लाइन में एक साइड से होगी एंड द अदर विल बी बोथ साइड्स, इस साइड से भी. तो मेन लाइन के राइट एंड लेफ्ट हैंड साइड्स में there will be two spectral lines which will correspond to magnetic spin होगा. So we could explain, इसकी explanation दी हमको दो physicists ने, एक का नाम था गोल्डस्मिथ और दूसरे का नाम था मिलबैंक. उन्होंने कहा कि जो अगर every electron हमारे पास जो है उसका एक intrinsic एंगुलर मोमेंटम है, उसी को हम स्पिन कहेंगे. Which is same for every electron, but apart from that, think spin, there is something called a magnetic movement which is associated with that electron. ठीक है, मैग्नेटिक मूवमेंट क्या हो गया? फॉर एग्जाम्पल एन इलेक्ट्रॉन इंडिविजुअली विल एक्ट एज ए मैग्नेट. इसका जिस तरह हमारे पास मैग्नेट होता है, मैग्नेट इन प्रेजेंस ऑफ मैग्नेट अगर दूसरा मैग्नेट लाएंगे इट विल अट्रैक्ट और रिपेल डिपेंडिंग अपॉन पोल क्या होगा. सो इन द सेम वे अगर स्पिनिंग इलेक्ट्रॉन है तो इट विल हैव द इफेक्ट कि इसका जो मैग्नेटिक फील्ड विल इंटरैक्ट विद द external magnetic field and it will have its own how it's going to orient vis-a-vis that field. So since electron was very small, it was considered उसका radius normally होता है 10⁻16 meters. So it was considered उसका कोई dimension नहीं होगा, तो it was considered जैसे classical particle है हमारे पास. Classical particle means it was a point particle. ठीक है, it was like that. But since we are saying that electron, if it has a magnetic moment, it's a small magnet, and the magnet is so if an electron is the magnetic field or magnet जो होगा and electron itself acts as a magnet, so you could explain जो इसकी जो spectral lines है ना which are more than one in number, that can be explained by this very thing. And further जो इसकी theory हमारे पास है it was explained by Dirac's theory. of how electron का अपना एक spin होता है, spin angular momentum जिसको हम कहते हैं, which is basically J. J is basically L plus S, which we study in the advanced courses in the quantum mechanics. But फिलहाल हम कहेंगे कि जो magnitude of जो electron spin है, it's basically S into S plus 1 ये S इसका ये value है. अब इसमें in your earlier classes आपने if you have studied Pauli's exclusion principle, have you studied it? है ना? No two electrons can have the same quantum number. जिसमें principal quantum number, azimuthal quantum number, magnetic quantum number है. जो नहीं हो सकता, we cannot have all of quantum numbers cannot be associated with electron. अब इसमें यहाँ ये है the thing is कि if we'll just rehash our how we used to study एक definition हमारी है इसकी say that no two electrons can be in the same quantum state. Okay, so that was the explanation for us. So each electron must have a different N, L or M. अब इसमें ये है कि the thing is that before we are going to explain इससे क्या चीज explain होती है this thing Pauli exclusion principle से. So there is another very important property, इसको हम कहते हैं something called symmetric and antisymmetric wave functions. तो जो हमारी जो ये Pauli exclusion principle है, why do no two electrons come into the same state? So we'll assume a fun more basic property of this state psi, wave function psi. उसकी property under certain exchange, it will transform, wave function will transform in a certain way, and it will transform in some other way. These two properties basically help us in explaining for us how we can explain Pauli exclusion principle at some fundamental level. ठीक है, तो हम क्या लेते हैं? We'll take symmetrization and anti-symmetrization as an idea. What is symmetric wave function and what's anti-symmetric wave function? तो symmetry जो हमारे पास है, for example, symmetry means what? जिस तरह हम कहते हैं ना reflection symmetry, inversion symmetry. For example, if you rotate along some coordinate system, it will not change, laws will not change. Or if you have forward direction of time and backward direction of time, laws of physics, mechanics will not change. Or if you rotate, or if you have a reflection symmetry, the laws will not change. In that sense, that's symmetry. In the same sense, जो wave function अगर हमारे पास है, कोई भी particle का, which is denoted by for 1, 2, so on, so that. So you can write them as psi 1, psi 2, so on and psi 1. अब जो हमारे पास basic है, we say that जो इसका square of the amplitude है, which is psi square 1, 2, it's equal to psi square. For example, if you take 2 particles, 2, 1. So if we have put 1 at 2 and 2 at 1, it will not lead to any change in our result जो हमारे पास है. How we can understand this? इसको हम कहते हैं symmetric wave function. अब in the दूसरी एक property है, if we change psi 1 to 2, if we change 1 to 2, it will lead to some exchange of sign. ठीक है, the wave function का value will be negative. अगर एक को दूसरी जगह will exchange particle 1 to 2 and 2 to 1, it will result in the change of sign of wave function जो हमारे पास है. तो अब ये है कि और if you for symmetric wave functions, for example, for symmetric wave functions, this equation you can say psi of 1, अगर हमारे पास psi of 1 is psi of A 1, psi of B 1, and for particles from B to 2, psi of 2 is basically psi of B 1, psi of B 1. So ये जो हमारे पास fundamental property है symmetrization और anti-symmetrization की, it fundamentally helps us to classify elementary particles जो भी हमारे पास हैं, electron, proton, photon, neutron, जो भी है. So all of these particles can have they will under some exchange interactions they will either obey this property or this property. इससे हमारे पास we can explain have one of the explanations of Pauli exclusion principle for symmetric states. For example, अगर हमारे पास symmetric states होंगे, तो symmetric states if you define symmetric states as psi of x is basically 1 by 2 is basically a normalizing factor, psi of A1, psi of B1 plus psi of B1 into psi of A1. So we have exchanged A with B, B with B, and ये प्रोसेस करने से हमारे जो टोटल स्टेट पे psi पे कोई फर्क नहीं पड़ता है. इसके बरक्स एंटीसिमेट्रिक वेव फंक्शन में what will happen is that psi of A, so it will be once we exchange psi A with psi B, there will be psi of A, psi of B. So once we change A with B, B with A, it will lead to some sign change. आप देखो यहाँ पर, so if A is B for symmetric wave functions, it means that psi of A आएगा, ये psi of A square आएगा, तो twice आएगा, ये psi by 2 आएगा. But if A is equal to B for antisymmetric wave functions, so it will lead to 0. So for these antisymmetric particles, we can say that Pauli's exclusion principle can be explained. This means that no two particles can exist in the same state. No two particles can exist in the same state. So you got the point. You are listening? Hello? Hello? So no two particles are in the same state. You can see from this very explanation. So इस broad जो characterization है, इसी से हम there are some particles which are called as fermions and some particles which are called bosons. So both fermions and bosons में हम कहते हैं कि उनका spin होगा 1/2, 3/2, 5/2. And bosons का spin होगा 1, 2, 3. So it's basically in a sense we don't see spin in that. We have not studied spin in that sense. How we define spin basically is the signals area. But at broad हम कहेंगे जो fermions and bosons को हम classify कर सकते हैं on the symmetric and antisymmetric property of wave function. Under some exchange, this property remains intact. And if you exchange a particle function, so its properties, the negative factor comes in, and you can explain Pauli's exclusion principle from this for antisymmetric wave functions as such. So this was this much. ठीक है, कुछ पूछा? Anybody you have to ask? Anybody have? कुछ पूछना तो नहीं है? Hello?
No, sir.
Okay. So यहाँ तक clear है ना? Yes. So we have done nothing. We have seen electron spin as a property from some basic fundamental property, and on that property, which is built upon exchange interaction, exchange हम करेंगे पोजीशन को चेंज करेंगे वन केस द प्रॉपर्टी रिमेन सेम अदर केसेस we will have a negative sign as a factor and that helps us in the classification of the nature में particles हैं either they are fermions or they are bosons fermions की ये है कि their wave functions they will not change sign under exchange interaction and they will change sign under exchange interaction ठीक है so this is a broad understanding. इसकी theory थोड़ा सा deeper है. You have to study spin as a property. So we'll study next semesters. तो अब ये है कि there is another thing, something called Stern-Gerlach experiment. If you have heard, Stern-Gerlach experiment भी है. It's also sort of experiment where what we are going to see is that. तो स्टर्न एंड गिलराफ ने दो एक्सपेरिमेंट किया था टू सी अगर कोई भी इलेक्ट्रॉन है या कोई भी इन एन इनहोमोजेनियस मैग्नेटिक फील्ड इनहोमोजेनियस इस वजह से कि अगर हम होमोजेनियस मैग्नेटिक फील्ड लेंगे तो ग्रेडियंट हर जगह सेम आएगा इनहोमोजेनियस में कैंसी इधर उधर होगा such that अगर हम कोई फॉर एग्जांपल मैग्नेटिक फील्ड को इनहोमोजेनियस मैग्नेटिक फील्ड में रखेंगे और स्मॉल मैग्नेट को so it will its components so it will randomly haphazardly जाएगा इस साइड या उस साइड जाएगा ठीक है but for example now here in our theory we have taken electron as a इसका अपना एक मैग्नेटिक मूवमेंट है तो अगर मैग्नेटिक मूवमेंट है अगर इनहोमोजेनियस मैग्नेटिक फील्ड होगा तो उसका जो इंप्रेशन और सिग्नेचर हमारे पास आएगा सो इन प्रेजेंस ऑफ मैग्नेटिक फील्ड सम कंपोनेंट्स विल बी इन वन डायरेक्शन सम विल बी अदर डायरेक्शन तो रैंडमली आएगा जो भी हमारे पास रिजल्ट क्लासिकली स्पीकिंग बट इट टर्न्स आउट जो इलेक्ट्रॉन्स हैं व्हिच हैव बीन देयर इधर उनका स्पिन अप होता है और स्पिन डाउन होता है स्पिन डाउन स्पिन अप मींस इधर दे विल हैव अ प्रेफरेंशियल एक डायरेक्शन में उनका इंप्रेशन स्क्रीन पर आता है दूसरी डायरेक्शन में दिस मींस दे हैव this is an example of something called space quantization so it's not that electron or charged particle or having a magnetic moment उसके जो when it is placed under inhomogeneous magnetic field it will have इसके components किसी भी direction में हो जाएगी randomly it is either in the up direction एक direction में in response to the magnetic field or in some another direction उसको हम up spin भी कहते हैं and the other one is down spin. So this is an important experiment which has been seen. So अगर इसका experimentation देखेंगे तो magnetic pole यहाँ से लेके दोनों साइड से ऐसा ये O1 होगा यहाँ पर and pass a beam through it and there is a photograph plate जिस पर इसका impression होगा. This is magnetic pole. This is beam of silver atoms. And so classically, you can have, it is assumed that हर जगह होगा इसका impression. But it has been seen, ये इसके दो spin up or spin down, ये preferential direction दो ही में आएगा. So this was this much. Yes.